All right. So yeah, today for our CHIME FRB Journal Club, we have invited Stefan Hackstein, who is a PhD student from University of Hamburg. Is that right? Oh, and I can't hear you now. I think you might be muted.
Oh, yeah, now I'm unmuted. So, well, it has been right until 2 weeks ago because I just recently finished my PhD 2 weeks ago.
Oh, yay,
Oh.
congrats.
So it seems that I'm using my wrong camera here. Maybe this way you can see me better. Okay. So can you hear me? You can see
Yes.
me? Good. Then I just have to share my screen and then we can start. We can start it.
Yep.
No. So now you should be able to see the paper.
Yes.
Yes. Okay, great. So yeah, hi everyone. I'm Stefan Hackstein, and Ryan can unfortunately not be here, but he invited me just 2 days ago to give a spontaneous talk about this great paper which just recently appeared on SGPH, and I thought it was a rather great idea because it seems that I've written this one, and yeah, just let me guide you through this, and let us go through the content here. So basically, what we do in this paper is we are looking at fast radio bursts, obviously, and we are trying to get an information about the intergalactic magnetic field. Basically, we are trying to get a measure on the intergalactic magnetic field, which so far we have not been able to measure. But there are a lot more things that are actually able. That we were actually able to do with the method we have been doing for this. So here we present a method to actually go and investigate the observables of fast radio bursts. Where for now we have been focusing on the propagation-dependent measures, so the dispersion measure, rotation measure, and the temporal broadening. And we are considering models for all of the regions along the nanosite and using Bayesian statistics and most sophisticated models for all of these regions. So some of the most sophisticated models, we actually derive rather realistic expectations for what we expect to observe with telescopes at Earth. So there are basically three main results that we have in this paper. First is that we can obtain lower limits on a rather significant amount of fast radio bursts that have an extragalactic DM of more than 400 parsec per cubic centimeter. We further look at intervening galaxies and see that they cannot all account for the high scattered fast radio bursts, but we need to explain the temporal broadening that is seen in FRB cuts. That is seen in FRBs that you can find in FRB cuts using some of the other regions. We will go into this into more detail about this later on. And the main result of this is that that I could show that we will be able, with a fast radio burst in the near future, to refine our current upper limits on the strength of the intergalactic magnetic field and actually do a bit better than this. But we'll talk about this at the end. So, as I said, we are presenting here a Bayesian framework, so a method which considers all of the different regions along the line of sight. So we consider the intergalactic medium. Of course, we are interested in this. We account for the host as well as intervening galaxies, as well as for the local environment of the progenitor, so the circumburst environment. So now for the FRB progenitor, since the observation of SGR 1935 this summer, this provides a very strong evidence for magnetars as a sources of fast radio bursts. And in this work, we are assuming magnetars as the only source of fast radio bursts. So FRBs are great cosmological probes. I don't need to convince you about this. So we know we have so far localized a few fast radio bursts, and we see that they can reside in dwarf galaxies, but also in supermassive ones. They can reside in starbursting galaxies, but also ones with very old stellar population. So basically, we cannot simply pick a particular model of a host galaxy, but we need to take a whole ensemble of all possible galaxies that is out there, and this is what we do in this paper. So furthermore, in order to learn something about the distribution of measures that arrive at Earth, without knowing where the individual fast radio burst resides, so at which redshift, from which redshift it comes from. So we have to somehow estimate the fast radio burst distribution, redshift distribution, and we take some very realistic estimates from this using the FRB copy code by David Gardenier. And we put this together with models for all regions along the line of sight to get very good estimates on what we expect to observe at Earth. So it has been shown already by Akahori and Vatsa and others that the dispersion measures and rotation measures potentially signal information about the intergalactic magnetic fields. And I've been investigating this also together with Brian in the paper in 2019, where we basically started to develop this framework and where we could show that we can tell apart very extreme models for the origin of intergalactic magnetic fields. And now we refine this modeling and also refine the machinery to look at this and see what the observed rotation measures do tell us about the intergalactic magnetic fields, or actually how many do we need to look at in order to learn something. So as I said, we are counting also for intervening galaxies, and we are going and we have learned something about them too. And basically, to do all of this, as I said, we have been producing a Bayesian inference framework, which has been put together in a software package, Python open software package, preferable, short for probability estimates for fast radio bursts, to model likelihood estimates. And this provides you with a preferable way to interpret fast radio bursts. And I hope I can convince you to take a look at this machinery and maybe see if you can apply it in your own research. So as I said, we, for now, are looking at the propagation-dependent measures. So we are looking at the dispersion measure. I don't need to explain this to all of you, as you are all experts in fast radio bursts, and this is the key observable of all of them. And the dispersion measure is pretty much dominated by the large scale, by the large scales in the low density universe. So basically it gives us a very good information about the distance, or a rather good information about the distance of an individual fast radio burst. So furthermore, we are looking at the Faraday rotation measure, and this gives us information about the magnetic field along the line of sight. Now, the problem in interpreting rotation measures is that significant contributions are expected from all of the regions along the line of sight. And if we want to learn about one region, we have to count for them all. To make this even more complicated, the RM can be positive and negative, and thus different regions can cancel out each other. And we actually have to account for this in our calculations, and yes, we do so. So the third observable that we are looking at is the temporal smearing, so the broadening of the pulse of fast radio bursts. And basically what is so special about this is that the effective lensing distance of the lensing material is of interest. So the closer to the center of the line of sight the lensing material, the stronger is the scattering that we observe. So this is why we expect that intervening galaxies are dominating this temporal broadening, and we are trying to look whether this temporal broadening does allow us to identify lines of sight with intervening galaxies, and whether we can find all of these lines of sight using only the temporal broadening. So let me take a short sip. So yeah, as I said, for this we use a Bayesian framework, which is put together in a Python software package. Here you can find the GitHub link for this. And yeah, here I now shortly go through the way of how this actually works. So basically we take models for all of the regions along the line of sight, as I said. And so we first look at an individual model and perform a Monte Carlo simulation in order to estimate how likely do we see different values contributed from these regions. Now, once we have done this for all of the individual regions, we can combine these the contributions simply via convolution or by doing another Monte Carlo simulation. And by this, we can then predict the expected measures for a full line of sight scenario, accounting for all of the regions. And this can then directly be compared to observations of fast radio bursts for which we know the redshift. So we can then interpret the measures and see what this tells us about the models along the line of sight, or about the regions along the line of sight. Now, since we do not know the redshift for most fast radio bursts, we need to take realistic assumptions on the redshift distributions in order to predict what is the distribution of values that we expect to see at Earth. And yeah, as I said, we use FRB Poppy to get realistic information about the estimates on the fast radio burst redshift distribution, and together with the expected distribution of a particular measure at a given redshift, doing the redshift integral, we arrive at the prediction, what is it that we actually expect to observe at a terrestrial telescope. So here we are looking only at one measure, for example, the dispersion measure. And basically what we do is we look at a particular redshift and we throw a dice to see what is, throw a single dice in order to see what is the DM that we expect from here. Now, if we want to look at the DM and the RM together, we're basically throwing two dices, and thus we have to multiply the likelihood for these two, and this is what we then actually use to compare these two things together, which allows us to get the full information of the observation rather than to reduce it to the ratio of measures. So last but not least, in order to compare different models to each other, we use the Bayes factor, which basically tells us how much more likely model 1 is reproducing the data than model 0. And basically, if we have a value more than 100, this means that model 1 is 100 times more likely to explain the data than model 0, and thus model 0 could be ruled out with 99% certainty. So in a short summary again, we estimate what do we likely expect from a particular model. Then we combine this different regions. We put it together with estimates on the redshift distribution, and this gives us the expectation for what we see at the telescope. And by using the Bayes factor, we see which of these models do best explain what we actually see at the telescope. So are there any questions up to here?
So I have one.
Yeah.
I think you've already discussed this, especially if you are considering the host galaxy. We know that the RM and DM are somewhat correlated. So when you're choosing a model, specific rotation measure model for host galaxy, are you also, however, basically taking into account that RM can be negative as well?
Yes, we are taking this into account. Basically, by taking we are looking at absolute values for the RM to get a logarithmic distribution of them, but then we mirror this also to negative values, and in the convolution, we actually account for this by doing it this way. So we do convolve also with negative values.
Yeah, actually, what I want to ask is, in the case of Milky Way, we know that even within 1 degree, the RM changes significantly. So
yeah.
There is, because of H2 region and all, there is a change. So I'm just wondering that because you are also assuming, I think Pyro and Gansler magnetar ambient environment model. So do you also account, like, do you also take a Bayesian sort of prior for this and then include it in your likelihood?
Well, we do not account for the Milky Way so far, assuming that because of the fact that for all of the other regions, we need to do a statistic interpretation because we don't know what exactly we are looking at. But for the Milky Way, we know exactly in which direction we look, and we have other rotation measures, the Opperman map, for example, which tells us what is the Milky Way contribution. So we do not look at the Milky Way here, assuming that we can reduce the Milky Way foreground.
Okay, thank you.
But yeah, this is already some model questions, and this is now what we'll come to right now. So I'll shortly give you an overview of what is the models that we're actually looking at. And as I said, we are looking at the intergalactic medium. We are looking at the intervening galaxies. We're looking at the host galaxies, and we're looking at the circumburst environment, and assume that fast radio bursts are produced by magnetars. since we are most interested in the I was most interested in the intergalactic medium, we start with this. And for this, we use constrained cosmological magnetohydrodynamic simulations that reproduce our local universe. And here you can see a picture of this. So this is the distribution of matter, and you can see, you can find the most prominent structures in our local neighborhood around the Milky Way here. So it is these simulations that we do. They start from a rather high redshift with a uniform universe, and then we follow the structure formation as well as dynamo amplification processes, and thus get a very good estimate on what is the distribution of structure as well as what is the shape of the intergalactic magnetic field here. And in our last paper, we have been trying to tell apart two flavors of the origin of intergalactic magnetic fields, which can either be of primordial origin, and in this case, the magnetic field would span the entire universe and would basically survive to the present day out in the voids. You can see this in the left case, where we have very strong magnetic fields in the low density regions. And this is opposed to the right part, where we assume that the first magnetic fields were produced by astrophysical scenarios, so with or by the first stars and galaxies that formed, which then expanded their magnetic fields out into the universe. And in the latter case, the voids and low-density universe will contain much, much less magnetic fields. So we have been showing that fast radio bursts are able to tell apart these two models, and here we are improving the modeling of the of the intergalactic magnetic field. So here are the first plots that show you the average dispersion measure or rotation measure as a function of redshift, and this should only show you that the average estimate does fit with other more simple descriptions of the mean. However, if you're looking at the distribution, then at the distribution of the m's, what we are doing here, we're not looking at the average, but at the distribution of all measures. This is also sensitive to the this can be a non-Gaussian, and thus we need to account for the large-scale structure and the inhomogeneities in the universe, and this does show in the distribution of dispersion measures that we see. But more strongly, it also shows in the rotation measures. So yeah, the minimum resolution is 30 kiloparsec in here, so we do not resolve individual galaxies. So in this simulation, we then take lines of sight and calculate the line of sight integrals in order to get our estimates on the dispersion measure as well as on the rotation measure. So let's not talk about the baryon content, because this is the content of another paper. And basically, what you can see in this plot here is the comparison of the primordial and astrophysical case. I've been just showing you this. So here, these two models are here plotted for the medium magnetic field as a function of overdensity. And these two models basically span the range of what we think is possible in our universe. And what we actually would like to do is to measure the intergalactic magnetic fields out in the void, so in the very left part here. But this does actually contribute much too less to the rotation measure and is not accessible to terrestrial telescopes. But instead, we can learn something about the intergalactic magnetic fields also by learning something about the slope of this function. And so we use a very simple parameterization, a simple power law, and try to constrain the slope of this function in order to provide constraints on intergalactic magnetic field models. So basically, now we make predictions for all of these different dotted lines here and try to see whether we can find a difference in the signal in fast radio bursts. So we're not gonna talk about this. Now, the next model that we have is the host galaxies. And as I said, we are not using a particular model for this, but we take a whole ensemble of galaxies. And for this, we make use of the results of Lacey, 2016, who studied the evolution of galaxies with the Galform model. And what they provide is the best fitting initial parameters for galaxy formation theory that reproduces all kinds of different observables for our for the galaxies we find in our universe, and this can be used to get a large sample of galaxies that present the ensemble of galaxies in our universe, and this is what we use. Now, Luis Rodriguez, a co-author of the paper, he has been using this set of models and nonlinear turbulent mean field dynamo theory in order to tell us what is the coherent magnetic field we expect for this galaxy. And with this description of the magnetic fields, together with the radial profile of the electron density, we can again reproduce line of sight integrals and get an expectation on the host galaxy contribution. We take a sample of a few million galaxies that are axisymmetric, and by this, by different morphologies and different sizes, we can reproduce more than 90% of galaxies in our universe. So this is a very representative ensemble of galaxies here. We use the very same ensemble of galaxies also to account for the intervening galaxies. And here we make a realistic estimate on the intersection probability, taking into account the density and the size of the galaxies. But let's not go into too much detail here. Because, you can see here the average number of galaxies along a line of sight as the function of redshift. So redshift of the fast radio burst. And this agrees rather well with earlier works by J.P. Marquardt. So, for the local environment, as I said, we are assuming that all fast radio bursts are produced by magnetars, and we take the Pirro and Gensler model and using a Monte Carlo simulation to obtain the probability estimates for the dispersion measure and rotation measure. And actually, I've been expanding this model also to use the scattering measure, which can be then used to calculate the temporal broadening. So last but not least, as I said, we have to somehow model or estimate the distribution of fast radio burst redshifts. And this has been done with the fast FRB poppy code by David Gardenier, which is exactly pointing to, exactly built to do exactly this. So to get the distribution of fast radio burst redshifts and other properties. But I was mostly, we were only interested in the redshift distribution here. Expected to be observed by different telescopes. So we basically assume three different intrinsic distributions, either following a constant co-moving density, following the stellar mass density, or following the star formation rate, and see how these different intrinsic distributions do affect our observations. And then after we using this functions for the density, we sample a few million fast radio bursts and the intrinsic properties, and then apply the selection mechanisms of the telescopes. And so starting from the intrinsic distribution of fast radio burst redshifts in the upper plot, we arrive at the expected distribution of redshifts for the other kinds of for different kinds of telescopes that I guess you all know. So with that, we are through with all the models and the basic, and the basics of the methods. And now we can look into the applications of this. And I hope I can convince you with this that using this, that you do not want to go through all of this everyone again and again, that we wanted to use some kind of machinery that takes the work off our shoulders. Well, yeah. However, so let us have a look at the applications that we were so far able to do with Preferable. And the first is that.
Okay, so just a quick question. You mentioned the selection biases of the different instruments.
Yeah, exactly.
Bit more about how you, where you got those and exactly how you handle that, because that seems important. And
yeah, okay, so basically you can find all of the details in the paper by David Gardenier because they are making an investigation to try to make out these parameters. So first, they take the parameters that we expect only from knowing the techniques of the technique of the telescope, and then they take this together with intrinsic properties of the fast radio bursts, trying to varying these intrinsic properties in order to reproduce the data that is observed by the different telescopes. And we use their best fit parameters for the different telescopes that they provide. So if we want to have, so we didn't do their analysis again, but only took the best fit parameters. But the most prominent difference between the three telescopes is that they have a different gain, and ASCAP can only observe rather bright sources in comparison to CHIME and Parkes, and this is why ASCAP can only see fast radio bursts at a rather low redshift, so below redshift 1, as opposed to CHIME and Parkes, which can observe much fainter bursts and so can probe a higher redshift. Is that enough of details for you?
Can I see the top plot? It's cut off.
Yeah, sir.
Oh, that's the intrinsic.
So that is the intrinsic one. So this is before the selection effects, and then these fast radio bursts all have some properties. So they have a pulse width, they have luminosity, and so forth. And so then the selection effects of the telescopes are applied. So can they actually see these fast radio bursts? And as you can see, many at high redshift cannot be seen by the by the telescopes, and so we only select those the distribution which is actually accessible to the telescopes.
Right. Okay. Thank you.
Great. So if there are no other questions, let's go to the applications. So first, we want to identify line of sights that have intervening galaxies along the line, that have additional galaxies along the line of sight. And for this, we are looking at the temporal broadening and want to see whether this can be a very simple tool to identify all of these lines of sights. So with this, we are looking at 3 different scenarios. The dashed dotted line shows a sample where we only have lines of sights with intervening galaxies, and this is opposed to the dotted variant where we only have line of sights without intervening galaxies. A realistic combination of the two is the solid line, which shows then the combination where we have a realistic combination of lines of sights with and without intervening galaxies. And what you can see in this plot is that there is some value of the observed temporal broadening, which can only be associated with intervening galaxies. So according to our models, there seems to be a particular value of temporal broadening above which there has to be an additional galaxy along the line of sight. And yeah, in a realistic, you can see here that the realistic combination of the two does only show a rather low amount of lines of sights above this particular value. So it is in the percent regime. So let's have a closer look at the numbers. So since ASCAP and Parkes are observing at the same frequency, they are observing the same border of 0.06 milliseconds, which marks the minimum temporal broadening, which is certainly associated with an intervening galaxy. So CHIME, looking at a lower frequency where the scattering is more severe, has this border at 1.8 milliseconds, as you can also see here in these plots. Now, taking this as a harsh, as a very strict difference between, so being sure that all temporal broadenings above this value are sightlines with intervening galaxies, we predict that about 30% of all sightlines with intervening galaxies will be identified. So all of the rest show temporal broadening below this, though there is an intervening galaxy along the line of sight. And taking into account all the the realistic combination, we find that 1 to 2% of fast radio bursts should show these high temporal broadening based on due to an intervening galaxy along the line of sight. However, when we look in the FRB cut, we find that there is a magnitude more. So intervening galaxies, only by the number, can never account for all of the temporal broadening, for all of the high values of temporal broadening that we observe in the fast radio burst listed in a FRB cut. So this suggests that there is another part along the line of sight which does also produce a high amount of scattering. And actually, while taking a short look into the appendix, where you can find a rather nice set of plots here, you can find what is the expected contribution from the local environment, from the host environment, from the intervening galaxies, as well as from the intergalactic medium. So their expected contribution to what we see at Earth. And on the left, you can see dispersion measure. In the center, you can see RM. And on the right, you can see the temporal broadening. And we only focus on this for now. You can have a look at the other ones later on. We can see that, yes, so here you can immediately see which of the different regions does dominate particular observable. And looking at the intervening galaxy plot, we see that this has a rather significant likelihood of showing very high temporal broadenings, which cannot be produced by the host environment and only in some very minor cases by the intergalactic medium, but it is only the local environment which can produce broadening at the same scale. And so we are likely looking at some more turbulent and some more dense local environments that we have been assuming here. And yeah, this is basically one of the main results. But the main conclusion is that intervening galaxies alone cannot account for all of the temporal broadening that we see, but it is likely that the local environment is producing a very significant amount of them. So about 90% of this high temporal broadening.
Did you, you may have said this and I missed it, but Vedantam and Finney had a paper where they considered circumgalactic medium scattering. Is that something you accounted for?
So no, it is the circumgalactic medium which we are not accounting for. And if you would account for this in intervening galaxies, then this might also explain some of the additional, or many of the temporal broadening. So yeah, this is also another solution.
Yeah, and some of the scattering could actually be like unresolved structures in the burst. I mean,
yeah, exactly.
Yeah, I'm pretty confident that not all the broadening is actually scattering.
Yeah, sure. This is this might also be something, but yeah. So this basically confirms my impression that it is something about the local and either about the local environment or the progenitor itself. Yeah, or it is the circumgalactic environment. So basically, we need to. The basic conclusion is we need something else in additional to the intervening galaxies. So there are a lot of solutions, of course.
So Stefan, when you are saying intervening galaxy, you are only considering the scattering that happens when the FRB sightline actually passes through the ISM of the intervening galaxy rather than the halo.
Yeah. Yeah, exactly. So we have an elliptical model for the galaxies that contains the basic, so that contains the disk of the galaxy, but not the halo. And so it is only the interstellar medium. Exactly.
Isn't it that, but I don't know, maybe I'm wrong here. I had this opinion that till redshift z equals to 1, the chance probability of an FRB line of sight interacting or passing through the central means 1 plus minus or around 5 to 10 kiloparsec of circle radius is very small. It's only when you consider one virial radius, sorry, when the whole one virial radius, then this chances that basically passing through a host galaxy.
Yeah, so
Because of extension.
speaking in terms of the viral radius, we take into account, I think it was a bit more, something between 3 and 4 times the viral radius of the galaxy, and this is all of the galaxy that we account for.
Okay, because that would be a part of CGM, circumgalactic medium instead. Isn't it?
Okay. I think we really had the border, we were choosing the border that we are not touching the circumgalactic medium, but only the galaxy itself, but the galaxy out to its very borders. So basically the whole disk is in there, but not much more.
Cool, thank you.
Okay.
I have another question.
Yeah.
For the ISM of the host galaxies, I see that, so you use those equations 3 and 5 in the paper. So basically they're models for how much scattering there is given some location in the galaxy, I guess. But do you have any feeling for how well that model could describe, for example, our own Milky Way, where we know much more about the scattering properties?
Well, here we have an ensemble of a few million galaxies of different sizes, different morphologies. I bet you could find one which matches very well the Milky Way, but we have no searching for this because we have models that try to exactly reproduce the Milky Way, and they do this much better than this rather simplistic model with only a radial profile that we are using here. So we have millions of galaxies with a radial profile. It is not a very good it's not a very good representation for what we all know about the Milky Way, but it gives us a very good statistical estimate on what we expect from extragalactic, so from other galaxies.
So is it a single model for like ellipticals and spirals? Is that what you're doing?
No, as I said, there are millions of models, millions. So we have millions of models with different morphologies, and so we combining a bulge mass as well as the mass for the disk and the size for the disk and the size for the bulge. You can then combine different sizes and of these two and masses to form either a spiral, to form either a disk galaxy or an elliptic galaxy or
right, but the scattering properties are sort of uniformly distributed amongst all these models. Like you wouldn't.
No, the ensemble is produced to reproduce our observations in the universe. So it just reproduced the galaxy stellar mass function. It does reproduce Tully-Fisher relation, all kinds of luminosity functions, and so so we have the ensemble of galaxy models is that way that we have most of these galaxies are Milky Way-like galaxies, as we expect from the galaxy stellar mass function, and we only have rather few dwarf galaxies, but all of them are in there.
Okay, I'm sorry, I understand.
And,
okay, great.
And sorry, the position of the FRB within these galaxies is just randomly chosen for each one of your models.
So it is chosen according to the molecular density, which we take as a tracer for star-forming regions, which are the most likely regions to find magnetars or young magnetars.
Yes, but yeah, I'm a bit curious because in our own galaxy, the RM and the M of the magnetars we observe change of orders of magnitude, right? So, I was curious if you were considering like magnetars at the center of the galaxies, or distributed randomly, or
so distributed randomly, basically.
Okay.
But you mean randomly in a disk, not randomly. I mean, they couldn't be in the halo, I suppose.
No, it is randomly distributed in the disk following the molecular gas density.
Right. Okay. Thank you.
Great. Thanks for all your questions. So let's go to the next application, which is trying to infer the redshift of an unlocalized fast radio burst. And what has so far been done in literature is what you can find in the top two plots here. So basically the left plot, here we look at a particular redshift and see what is how likely do we see different values of the M for a fast radio burst coming from this redshift. Now we do this for increasing redshifts, and thus you can see that higher redshifts are associated with higher values of the M. Wow. Now, when you observe a particular fast radio burst, for example, the Spittler burst 121102 with a particular dm, you can simply extract all the function values and thus get a distribution of possible redshifts for this fast radio burst. And so we all know how to get an estimated value from a probability function. We can even get a deviation, go home, have a cup of tea, because we've just roughly localized the fast radio burst. As a Bayesian, I would advise you to look more closely at the assumptions that we put in here. And here we implicitly assume that all redshift bins are equally likely to host fast radio bursts. However, this cannot be true. This is not only because we need to account for the selection effects and for the source history, but the most prominent factor is that the probe volume does vastly increase with the redshift. And so when we take this realistic, all of these into account in realistic estimates on the redshift distribution, we multiply this in according to Bayes' theorem. So you can find this here, or actually also down here again. And this then gives us a more realistic distribution of where do we really expect this fast radio burst to come from. And due to the increase of the volume with redshift, it is much more narrow at the low redshifts than the previous one. And it is this fact, which is model independent, which allows us to derive lower limits on the redshift of fast radio burst with a dispersion measure above 400 parsec per cubic centimeter. And these are 3 sigma lower limits. Of course, for an individual fast radio burst, this you can never be completely sure that this is not a very strong local contribution that can be of several thousand parsec per cubic centimeter, but this only with rather low probability. And thus, for a sample of fast radio bursts, we can definitely show that some of them do come from cosmological distance. And yeah, you can get lower limits which are useful when looking at several fast radio bursts. And it is actually the table 1 you can find in the beginning of the paper. I don't know why the monthly notices put it up there. You can find estimates for those fast radio bursts where we can provide lower limits. So far, so good. Now coming to what I consider the main result of this work, which is about inference of the intergalactic magnetic field. And remember that we want to use dispersion measures together with rotation measurements of the unlocalized fast radio bursts in order to constrain the index of the magnetic field over density relation, the slope of the function. I've been showing you this before. I will show that again to you in a few minutes. And
I'm sorry, can I ask a question? It's related
Sure.
to just while estimating the lower limit of the redshifts, what Milky Way halo model you used?
so here we are only looking at the extragalactic dispersion measure. So basically, we've been taking what in the FRB cat you can find the observed DM together with the estimate on the Milky Way based on the NE 2001, I think. And yeah, we simply use this as a good estimate.
So okay, so you didn't incorporate the uncertainty
No.
in both Milky Way halo and IGM. Okay, cool. Thank you.
Thanks for the question. Okay, so these different values of alpha do represent different strength of the intergalactic magnetic field. And here we are looking at the cumulative distribution of rotation measures expected to be observed with CHIME. And what you can see is that indeed, the stronger the intergalactic magnetic field, the more rotation measures do we observe from 0.1 to about 2 rads per square meter. And actually looking here at the differential distribution, we can see that the shape of this distribution does tell us something about the intergalactic magnetic field. And now you might say there is only a very marginal difference between all these functions. And actually you're right, but remember that those fast radio bursts at the farthest distance are most revealing about the intergalactic magnetic field, because they take up most information about this. And these fast radio bursts are associated with high dispersion measures. So when looking at the dispersion measure together with the RM, we can learn quite a lot more, and there will be a much bigger difference between the different choices for the intergalactic magnetic field. So here again, this is the actual equation that we use. And let me give you shortly give you an intuition for this equation. Looking only at the RM-free part in the integrand, we can see that this is exactly what we used in order to infer the redshift of an individual fast radio burst. So basically what we're doing here is, for an individual fast radio burst, we first look at the DM, see what this tells us about the redshift. Once we have this information, we take this together with the RM and see what this tells us about the intergalactic magnetic field. So what do the fast radio bursts we have seen so far tell us about the magnetic field? Not too much, because we haven't seen enough of them. But instead we have to ask the question, how many fast radio bursts do we need to observe with CHIME in order to be able to put better limits on the intergalactic magnetic field? And so for this, we have been producing a mock sample, assuming the weakest of intergalactic magnetic fields, and try to see how many fast radio bursts do we need to see in order to rule out other values of alpha. Remember that the Bayes factor of 0.01 means that our probed value of alpha, or a probed intergalactic magnetic field model, is 100 times less likely to reproduce the data, and thus can be ruled out with 99% certainty. So what you can see in this plot, the Bayes factor as a function of a mock sample size, that it requires us 1 to 2,000 fast radio bursts in order to rule out the first value of alpha, so in order to ruling out the strongest possible intergalactic magnetic fields. This means with about 1,000 fast radio bursts, we can confirm and slightly refine our current upper limits on the intergalactic magnetic field. This is great. However, following this ruled out line further, you can see that all the other values of alpha, so all the other possible intergalactic magnetic field strength, go into the ruled out region. And this means that using fast radio bursts, tens of thousands of fast radio bursts will be available once the SKA comes online, or when CHIME has been looking for a bit more than a decade. Then we will be able to push the upper limit down to the region of the lower limit, and thus in the near future, with the methods that I'm providing in this that we are providing in this paper, you can use fast radio bursts in order to exactly measure the intergalactic magnetic field, and thus tell where is the origin of intergalactic magnetic fields. And I think this is a rather great bottom line for the PhD that I received 2 weeks ago. So yeah, I think I already took quite a lot of your time, so I will not again go through the summary. And yeah, well, shortly we have shown you that intervening galaxies cannot account for all the temporal smearing. We provide a way to estimate redshifts and provide lower limits for a big sample of fast radio bursts. We have shown that fast radio bursts will allow us to measure the strength of the intergalactic magnetic field once and for all. So I'll be happy to take any further questions from you.
Thanks, Stefan. This is really an impressive work, and it's going to be very useful. Have you tried the last plot that you showed about the limits on the magnetic fields in the AGM with fast radio bursts with an accurate position? How will it change, if any?
So for fast radio bursts, those fast radio bursts with an accurate position we so far have, these mostly come from rather low redshifts, and so they are not too telling about the intergalactic magnetic field. So and we are far away from thousands here, so they do not tell us anything about the intergalactic magnetic field
Yeah, I'm
right
sorry,
now.
I wasn't clear in my question. Let's say that we have 1,000 fast radio bursts localized to
Yes.
single galaxies.
So, of course, here we're using the dispersion measure as an estimate on the redshift, and so we get some uncertainty involved in this. If we have an exact localized redshift, then of course this will improve our interpretation, and this will reduce the actual number that we require to put the constraints. So, with localized fast radio bursts, much less of this will be needed, but I haven't looked at the exact number.
Perfect, thank you.
Stefan, so
yeah.
First of all, thanks a lot. It's very informative talk. It's great work.
Thanks.
But I have a question. You said that even intervening galaxies cannot explain the excess or very high scattering. Now, if we assume that the local medium is the one that is majorly, or as you said, around 90%, at least in the 90% of cases, it's the local environment that is contributing to the scattering. So in that case, do you have a prediction for rotation measure as well? The host contribution, the host contribution to the rotation measure? Because I expect that those high intense scattering regions are located majorly in the high magnetic field.
Mm-hmm. So yeah, so you have to look at this at a very explicitly in order to get a very a good estimate on this. But generally speaking, if you have a local environment that is responsible for this, then of course it will be a much denser environment, and only the more density of the environment will produce higher dispersion measures and higher rotation measures together. And so, yeah, of course, if we are looking for a local environment with a stronger contribution to the scattering, then the contribution to RMs and DMs will rise, and this will hamper our search for the intergalactic magnetic field, for example.
Thank you.
Thank you.
Well, so yeah, thank you once again, Stefan, for this amazing presentation. I think we all learned a lot from it. Also running out of time. Yeah, I wonder if there's more question. If not, then yeah, I think that's it for today. Great. Yeah, so thank you very much.
Yeah, thank you very much. Interesting, very interesting, and congratulations on your PhD.
Thank you.
All right then. Bye, everyone.
Goodbye.
That's it from congrats.